So first up, hello. Happy Thursday. Not rhetorical. Actually, hello. Thank you. Waving hands is also accepted. I updated the website, I think it was either yesterday or Tuesday, so I wanted to point this out, that I am officially punting on 2 of the examples that I had hoped to cover because we're not going to get there. So if you want to see 2 more examples of multivariate models using univariate software, one of which also uses path analysis, then you can visit the materials from the last time I did this class when I actually did get through at least some of it. Unfortunately, that means R won't be included. However, example 5A does have R for both the multivariate section and the path analysis section, which I called part 2, which we'll do next week. And all of the path model stuff that I'm working on now will have R if possible. So I'm building example 6A with a record new 4 different packages because SAS, Stata, R, and M+ will all fit path models with the multivariate normal assumption. The last one, however, I think is just going to be M+ based on the capacity to use full information maximum likelihood, but I'll have to verify that. So I am working on that. And you all are probably working on homework. Does that sound about right? And projects for other classes and final exams. And it's that fun time of year where everything's due at the same time. I know, but just think how good it's going to feel in like 3 weeks when everything is done. Because for better or worse, it will be over at some point. And it will be what it is. But for now, we're still making our way through. Does anyone want to ask about homework 5? How's the pancakes and crepes going? My homework is a means to procrastinate on other things? Yes. Yes, by all means, do this one first. There's something very satisfying about seeing the boxes turn green and knowing that you're making some progress. Except when they won't turn green, and then you want to punch to the computer or punch me. But you know what the rule is when that happens, right? After 15 minutes of trying, you stop. Ask for help. Does anyone want to ask about any of this? Talk about coding, parameterization, any of that? If you do ask for help, in this case, I would need to see like how you set up your variables, because there's different ways to do the coding that would result in different parameter estimates, which number you're stuck on, and the method you're using to get that analysis. I can always run your data and see what, and I have the database saved, of course. So, but in this case, it'll be helpful for me to see sort of all the pieces in order to help you troubleshoot. So, none of that? Nobody wants to be brave and ask questions? Or you're like, Lisa, it's Thursday. It's not due for like 6 days. That one?
Yeah.
Okay, that's fine. I'm just asking. I got the office hours later if anybody wants to come hang out. The other class is working on a homework that's due next week as well, but it's an easier one, relatively speaking. So I don't expect to be super busy in office hours. Okay, well, if no one wants to talk about that, then we can go back to the other stuff we were talking about. Shut this down to save some energy here. Do you want to look at our example some more? Mm-hmm. More practice with multivariate models and coding schemes and thus? So do you remember the story behind these data? 3 people from the same family, same outcome, measured across all 3 people, conservative gender attitudes with respect to how people should behave in a marriage. Higher scores mean you're more conservative. And we made our way through the stacking process. So a couple of you have mentioned that you're trying to do the stacking in R using tidyverse or some other way of doing that. If the program did it correctly, then any variable that was already there that you did not do any stacking to should be copied down the rows for that unit. So if that didn't happen, then you cannot use your data because it will kick out any rows that are incomplete. So like father's education here, in the original data set was 1 value for just the family because this was a family level wide data set. In the individual level data set where it's observation within family, dad's education is pasted across all 3 rows. So in this case, it would be person ID and experience that would need to be pasted across all 2 rows for each person. So that can be a little bit tricky. It's always helpful just to open your data after you're finished mutating it or whatever you're doing to it to make sure that it actually looks like it's supposed to. I find that is essential in doing troubleshooting, especially when using R when the error messages are not necessarily super helpful. By the way, I had another instance of an analogy to capital letters. For my other class, I couldn't get the same plot to work that I made you guys at the very beginning of the semester. And I was like, it worked before. What did I do? So I just put placeholders in the handout like, I can't figure this out. I'll fix it later. So I'm like, Jonathan, before you leave for AERA, can you please tell me why my R code isn't working? And it turns out that I was trying to plot the centered variable and not the original. So the x-axis values were incorrect, and that's why I couldn't see any of the plots. And that's almost as dumb as an error as capital letters versus lowercase letters. So that is to say, I'm right there with you with being a little bit frazzled and missing things sometimes. So let me help you if I can with respect to getting homework off your to-do list. So we had 4 ways of setting up an empty model with 2x2 combinations of whether or not a general intercept was included versus separate intercepts for each outcome, and whether or not you use the factor way of coding the variables so that the program does the coding for you as opposed to making the internal dummy or the external dummy codes. I prefer the latter for transparency's sake and also because it provides more flexibility. So that's what we'll do in this example. The version that I'm rolling with is the version I called 0C, which is this right here. So I wrote out the 3 dummy codes that I made, and those are going to be my custom intercepts for each outcome. That means that any differences between them are going to have to be linear combinations, such as set up here. And by the way, homework tip, the questions this time have different orderings as to which comes first. So I tried to write them so that the outcome that would go better would be after the versus. So like if you got trained in pancakes, then I want to know what your score is in crepes versus pancakes, and it would be the other way. So if you get stuck on something, check the sign. If you flip the sign, that means you have the coding for the -1 and the 1 in the wrong order. So if you have the standard error right but the coefficient's wrong, that may be your issue, is that this version of which was the 1 and which was the -1 might be off. So that's an easy way to check to see if you are in the right place. So that's what I'm doing. We did the empty model stuff, right? That sound right? Ready to talk about actual predictors? Okay. So model 1, then, meaning the first model that has actual predictors in it, I have the same setup with respect to the intercepts. So there's no general intercept in this parameterization. Let me make it a little bit bigger for you. Everything is attached to a dummy code. So the dummy codes act like switches to control how each separate outcome is being predicted simultaneously. So what I have done in the second line here is add the effect of the adult child's gender, and I have called that variable kid boy, meaning the effect of being a boy instead of a girl. And I have let that slope, so it's really just a difference between adult children who are women versus men, I let that have an effect on the dad's outcome, the kid's outcome, and the mom's outcome. So I would expect that potentially it would affect the child's own outcome. I wouldn't necessarily expect that it would affect the others, but I'm going to try it anyway. Because we don't know how many other children are in this family. All we have is one of them. So to put it in the code then, we have, in SAS it looks like this. So I have the 3 dummy codes, and then kid boy is attached to each of them. So note there is no predictor slope all by itself in this parameterization. It is always attached to a switch that controls whose outcome is currently being predicted. So like this term will only kick in if kid is 1, meaning that it's for that type of outcome. Same thing is true in Stata. Note that I have the no int here in SAS to shut off the general intercept and the no constant in Stata to do the same thing. And in R, I have the 0 here to shut off the general intercept, and I've got all of the terms here listed beyond that. So that means the model is going to directly tell me what the slope of kid boy is for each type of outcome. I can then test whether that slope has a stronger effect on the adult child that it is the gender for versus their parents. So I have a couple of examples here of different types of hypothesis tests you might want to do in this situation. So first is a contrast. Contrast is a way to generate an F-test that lumps multiple slopes together. So what I am lumping together in this case is actually two terms. This is one idea, and this is a second idea. Note that there's only one comma in the middle. So what it's doing is building this difference and then building this difference and testing both of them simultaneously. In other words, this is essentially the 2 degree of freedom interaction for whether the effective kid boy differs across the 3 outcomes. That's what I'm trying to get here. Then I have the separate differences for each of the 3 possible combinations, whether there's a larger effect of child gender on the kid than the mom, the kid than the dad, the mom than the dad. And then I threw a couple others in here. This is one I don't think you've seen yet. This is adding a new slope that combines the effect of the child's gender on the parents. So I'm essentially averaging the slope across those 2 outcomes. The way that I'm doing that in SAS is by invoking this divisor option. So at the end of the day, we only need a 1, 1. Basically, you can't have more than that, or the math doesn't work. So I'm cutting these in half by using this divisor option. And I have to do that explicitly in the other programs instead. And then once I have this idea right here versus this one, this is asking whether or not the joint slope averaged across moms and dads is different than the slope for the kid. So a -2 here, because these are going to sum to 2, and then I divide by 2, and the whole thing sums to 0 like it's supposed to. So in Stata, it looks much the same, except for we've got the test command to do the joint F-test for the 2 differences. And I've written these a little bit differently here. Like this is testing whether or not the slope of kids' gender is the same on moms as kids, and this is kids and dads. And so this is another way that you can compute a difference in slopes in their notation. Here are the individual differences. Here's the lumped difference. I did the math by cutting the divisor equals 2 by multiplying by 0.5. So I did the same thing by putting those in parentheses here. All right, any questions from SAS and Stata thus far? All right, R folks. In this case, I did GLHT to do the joint test of the 2 differences. It's still not willing to give me an F-test even though it computed it, and it did so correctly. So this is one set of slope differences right here between kid and mom. This is kid and dad. And then I have the set of differences, and it did let me put in fractions. So that's how I invoked the divisor option here. And for whatever reason, sometimes it turns my numbers blue when I copy the syntax over, and sometimes it doesn't. I have yet to figure out why that is, but fortunately that's just a coloring scheme and it doesn't actually matter on anything. So these are sort of the new concepts. You don't need to do anything complicated like this in your homework, but I wanted to just give you a flavor as to how you can ask any question that you can think of with respect to differences in slopes or what a slope is across multiple outcomes. All right. Any of that you want to hear more about, or you want to see what happened? See what happened? Why not? So what is this? We'll do a little vocabulary review. What are these numbers?
Variances and covariances.
Yes, they are. So this is for whichever outcome is labeled as first. That's the kids here. So this is the residual variance of the child's outcome after controlling for their gender. This is the residual variance of the mom's outcome after controlling for the child's gender. Residual variance for the dad's outcome after controlling for the child's gender. These are the covariances. And this type of structure where all the variances and covariances are estimated separately is called what again?
What?
What's the name for this type of structure where the variances get to be separate and the
Unstructured.
covariances get to be separate?
Unstructured?
Unstructured, yes. Another word you will hear for this is saturated. The idea is that it can't be wrong. You've spent all the parameters you possibly could to model the relationships between these outcomes and their variability.
I wanted to ask a quick question about that. So is it kind of the same concept as like degrees of freedom, like how many you're allowing to vary versus fixing certain values?
It is if you switch to degrees of freedom in an SEM context, where degrees of freedom is all about the number of variables in the model and not the people.
Okay.
So the way I look at this is that the data going into this are 3 variances and 3 covariances. I am just letting those be the model parameters. So there's no savings, there's no efficiency, but that means I can't be wrong. In contrast, I could tell it, why don't you make these variances the same, or why don't you make these correlations the same that create these covariances? So there's ways that you can make this structure simpler, and you do a likelihood ratio test to see if it hurt. Yeah, question?
And so if you were to make like the variances 1, then it would be a not very correct result because it's so different from like the values are.
Say that again?
So like if you were to go from unstructured to forcing the covariance to be a certain, would it be 1?
Well, you could force a correlation to 1, but that would cause problems.
I got those mixed up.
Yeah, so the big deal is that we're estimating something on these off diagonals. That's what makes this a multivariate model that adds dependency in. So this is the dependency between kids and moms, kids and dads and kids. It's in there. So we're changing the assumption of our residuals to not be independent with constant variance. Instead, we're letting them be dependent with not constant variance depending on which response we're predicting. Okay, Vladimir, do you have a question?
Yeah, so until now, we assume that this R matrix is the same for each set of observations. So
Yes, we do.
we have different groups, but we are assuming that those different groups, which are composed for 3 members, have the same R matrix.
Yes, we are.
Until now.
Until we're going to do that this whole example.
Okay. But then we can change this assumption.
Yes,
or
you
not?
can.
Okay.
The ease of doing so depends on what software you're in. But yes, there's a reason why, like it prints for this family, is because in theory, you can allow the R matrix to differ as a function of predictors. So if I had, say, divorced families versus not divorced families, I could allow them to have different amounts of variability within those groups. In the example that I don't have time for, I have younger and older adults, and in that example, I go through the process of testing whether the R matrix is the same across younger and older adults, and it turns out it's not, because the older adults range in age from like 62 to 85, whereas the younger adults are all 19-year-old, college sophomores in the psych class that had to do the study for course credit. So there's a lot more variability in one of the groups. But yeah, it's trickier to do this as a function of continuous predictors, but it is possible. So those are known as heterogeneous variance models. They're also known in the multi-level literature as location scale mixed effects models, where the location model is your typical multi-level model, and the scale model is using predictors to describe differences in variance. So not account for variance, but different amounts of variance as a function of predictors. So yes, you can make that different, but not today. And this over here is the correlation version. So we can see exactly how related our residuals are. And this will change after we add predictors to the model, because this is representing what's left over. All right, other questions? So we are in REML for our estimation method, residual maximum likelihood. That is only possible, by the way, for conditional normal outcomes. So there is no REML, for instance, in SEM, in SEM software, I should say. there is no REML in IRT or most general linear models. So the number of parameters here that it's counting is actually just the number of parameters in the model for the variance, because the fixed effects are treated separately in REML. They are not found. They are found after the variances are found with a formula. So it's not something that adds to the complexity of estimation to add fixed effects. In ML, we count everything because the whole function is maximized simultaneously, not just the residuals part. Just as an FYI. Here's the contrast that I wrote to describe the differences in the slopes. So it looks like, no, there's not a difference across the 3 family members in the effect of the child's gender. But more specifically, we see that the story looks to be that the child's own gender matters for their attitudes. If the adult child is a man, he has significantly more conservative attitudes. And by how much? I would say 0.28 on a scale of 1 to 4. So not a whole lot. I decided not to emphasize effect sizes in this class because it would be different for every single unit. I did it when it was sort of like, this is an odds ratio, this is that. One thing that I'm doing more frequently in my other class now is just taking this t-test statistic and converting it into a partial correlation. So you can use the results of these fixed effects to convert any of these slopes into R's or D's that describe the unique relationship. And that will hold so long as your t is valid. So it extends to a whole bunch of different kinds of models. So if you want code for that, I have some, because I figured out how to do that. But it does look like the child's gender matters for the child. The child's gender does not matter for their parents, which makes some sense because we don't know the composition of the family. And it looks like, based on the findings, that the difference between the slopes, though, is not significant. So even though the kid's slope is significantly positive, and the slope for the mom and the dad is positive but not significant, these tests down here, p equals 0.08, are telling us that this number is not different from these. So one significant and one not does not mean they're different. It does probably mean, though, that it wouldn't make sense to leave these 2 slopes in the model, given that they're not significant and conceptually we wouldn't expect them to be there. It does look like there's a marginal difference between them if you lump together the 2 slopes for the parents and contrast that with the slope for the kid. So those were the extra estimate statements that I had the divisor by 2 so that I could create the average slope for the parents and compare it by the kid. And this sort of illustrates the idea of multivariate models as a way to save power. Like if I found that these 2 numbers aren't different, I could put in 1 parameter instead. And then I'd estimate 1 slope instead of 2, which would save power. And it does indeed look like those numbers are very much not different. But since both of them are functionally not 0, or functionally equal to 0, I will leave them out of the model. So we're going to proceed with just the 1 slope, not the others, based on this. Okay. Any questions? So this is where, okay, go ahead.
In this
Psych.
case, for example, if you scroll up, please, we can see that the interaction terms are not significant. Can we remove those slopes from the model?
Yes, these are the 2 we're going to remove.
But that's an interaction. We have learned that if we add interactions, we have to maintain all the categories.
So here's the thing. So did everyone hear the question? Like how can we, so the question was, what about main effects and interactions? If we have an interaction term, don't we have to keep the main effects? We don't have any interactions in this model. This is a main effect. It looks like an interaction. I know. This is like linear models like on steroids here. This dad is not a predictor, like it's a switch, because it's controlling which rows get predicted by kid boy. So what I have here are 3 intercepts and 3 main effects. I don't don't think I have any interactions in this example because I thought this was busy enough. But of course I had to do it too in your homework, you know, because interactions are kind of my jam. I get to introduce them in the other class today, so I'm very excited about that. But yeah, the idea that the effective breakfast making experience would differ if you were trained in pancakes versus crepes. That's an interaction term. This is just one slope. An interaction is a difference in slopes. I could have parameterized the model so that I had interactions in it, though. That's the thing. What I have are 3 potential intercepts and 3 potential slopes. If I took out the dad here and put in a general intercept instead, then what I would have is a main effective kid boy and then an interaction with dad, and that would be an interaction because that would be telling me directly what the difference in the slope is between kids and dads, for instance. Instead, I'm setting it up so that I get the slope for all cases, and any differences in the slopes are down here. Okay, does that help?
Yes.
Yes, good.
Thank you.
Okay, go for it.
Is it possible to change the asterisk notation, or is that just by virtue of the program?
That is by virtue of the program. It is a hashtag in Stata, a star in SAS, a colon in R, and I think it's also a star in SPSS, if I remember correctly. In M+, you have to literally make the variables. You can't define interaction terms on the fly. And in classic regression type packages, you often have to literally make the interaction variables as well. You may also see parentheses sometimes. So parentheses are used to create nested effects. I tend to write them like this way because this is clearer to me. Like this is the effect for this outcome. I get confused as to what's nested and what with the parenthesis notation. But if you look at the SAS documentation, they like to do parentheses sometimes too. Okay, other questions? So now we're adding in own education. So the notation for this is kind of crazy because it's foreshadowing what's coming next. So here's my empty part of the model, 3 intercepts. Here's the lone effect of kids' gender on the kids' outcome that I'm keeping. So the subscripts that I'm using here, I have F and I. So the first number pertains to which family member it is a predictor for. I think, how did I do this? Yeah, which family level predictor it is and then which individual level predictor it is, I think. I'm trying to remember how I did this. I changed my mind and I go back and forth. But we have this new term right here. This is the effect of dad's education on the dad. This is the effect of kid's education on the kid. And this is the effect of mom's education on the mom. So I could have set up the model with one variable for education that was stacked just like the outcome was. But this way allows us to have each other's educations predicting each other's outcomes in addition. So I'm keeping the one effective gender here and then adding 3 new main effect slopes. The effect of each person's education on their own outcome. So they show up line continuer and Stata because I'm using old Stata. They show up here and they show up here. Otherwise the code is pretty much the same. So then if we look at the results, I've divided the old results from the new ones. So we have the effect of the child's education on the child, not significant. The effect of the mom's education on the moms, not significant. So moms with more education do not have different attitudes about gender roles in marriage, but the dads do. So the more educated the dad is, measured as years of education, centered at 12, the less conservative their gender roles are, gender attitudes are. So they become more egalitarian the more educated they are, which sort of makes sense. I'm not a human development and family sciences person, but I can play one when the time calls for it. So when I was building this, where this example originally came from, the question that was being answered in the original study was, what is the effect of dad's education on everyone else? Which I thought was an interesting question. So I added these two terms to answer that question. So I'm adding the effect of dad's education as a predictor on the kids' attitudes, and then dad's education as a predictor on the mom's attitudes as well. So this starts to get into what is referred to as actor-partner models for dyadic data. That's often used for pairs of people, often in relationships, but not necessarily. And the effect of your own predictor on your own outcome is called an actor effect. The effect of someone else's predictor on your outcome is called a partner effect. So these new terms that we've added here would be considered partner effects, even though this is a threesome and not a dyad. So then I added a couple of estimates here for differences, kid versus mom on the dad-ed slope, kid versus dad, and mom versus dad. So rather than putting in differences via interaction terms within the model, this parameterization tells me what is the effect for each person. That means I have to get the differences to go to figure out what if the slopes have different effects on different people. And same thing added for these two slopes here. Same thing added for the estimates, and then in R, picking up the second line here as well. And slope differences at the ends of the lines.
Lisa?
Yeah.
In that case, when you have the zeros and ones there, if we would like to see what is the effect of that at 12, for example, in kids, do we have to use only one?
Like just what it is?
If,
Like if I just want to know what is the effect on the kid,
exactly.
then yeah, it would just be 1, 1.
Okay.
Yep. Yep, the minus 1, 1 is used to create a difference in
The difference,
slopes.
yeah.
Mhm.
Okay.
And so this is the part that I was saying, if your homework, if you get the right standard error but the wrong coefficient, it's possible you have these two backwards relative to what comes first. So it's the direction of the difference that is incorrect. The significance and the standard error would be the same. And I made pictures. So I added, forgot about that. So this is the last model in the original version of this handout that I ever estimated. And it was for the context of this class when I was going to demonstrate it using path analysis. What I found is that this model doesn't actually fit very well. So the reason for that you'll get to see next week. But I wanted to also examine the idea of whether or not we are in reasonable territory by treating these data as multivariate normal. So the outcome that we're looking at is a scale score. It's an average across items on a 1 to 4 metric. So it is bounded. And the distribution of these are somewhat not normal. So at least the marginal distribution. So I wanted to check the conditional distribution. So I added code to do that. And I don't think we've seen that here before. So I added the word residual as a keyword in mixed, which spits out a whole bunch of plots. By the way, in your homework, you're supposed to be using residual degrees of freedom as well. I set the sample size large enough that it shouldn't matter, but to get the exact correct p-values across the programs, I couldn't get them in R using Satterthwaite. So I had to switch to residual. So if the word residual would go here in your homework, it would go here in Stata, and that's just what happens in R, whether you like it or not. In Stata, then, to get plots of residuals, I did these two. So I asked to save the predicted outcome for each person, and then I also asked it to save standardized residuals, and then I made a histogram of the residuals and a scatter plot of the residuals against the predicted values. And I figured out how to do this in R as well using the predict function. So we're predicting adding a column to the data set that has the predicted outcome for each person, as well as the predicted Pearson residuals for each person, throwing in a histogram, and then throwing in a scatter plot of those so that we can check out whether multivariate normality is a reasonable thing for this model or not. Okay, any other questions on the setup? All right, then here are the 3 effects of dad's education on each person. So the first one we had before. I also left in the effects of their own education as control variables, because what they wanted to ultimately say is that dad's education has an incremental effect beyond your own education in predicting conservative marital attitudes. So I had to leave these in order to make that claim. So here's dad's education on dad. We had that one before. And here are the 2 new ones. And it looks like dad's education has no relationship to the attitudes of their spouse or their child. And apparently that was unexpected. So I have a results section for all of this stuff. And then I have some pictures for you. So this is what came out of Proc Mixed specifically. It has a nice little summary here. These are the Pearson residuals. What do you think? What do we think about this? Normal is a reasonable thing? Exactly. We're all making the same head movement here in class. It's not like terrible. I mean, it's not like they're supposed to be on the little line here. Although honestly, these quantile plots are never useful to me. I don't find them intuitive, but I can look at this and be like, well, there should be more over here and there's not, and there should be a little more over here that there's not. And the reason for this stacking, by the way, this is a bounded data problem, right? The outcomes can't go past 1 to 4. Heterogeneity of variance. I mean, it's a little bit squishy over here, but yeah, more variance in the middle, less variance on the outside, less variance on the inside. That's a bounded problem. So, like, maybe boundaries are potentially problematic. I did look at the distribution of the predicted outcomes, though, and they did all stay in bounds. So I didn't have any predicted outcomes that were impossible. So this is kind of the problem, I feel like, when we're trying to decide if something is good enough. There's not really tests for this, and the ones that they do have are super sensitive to sample size and other sorts of issues, and so people tend not to rely on them. More pragmatically, I do not know of a single way that I could fit a multivariate model with a beta binomial distribution, conditional distribution, and a link function that is a, what do you call it? What's my word? Starts with a B. Binomial. The logit link function. There we go. I don't know how I would do this, to be honest with you. I would have to like write it up in JAGS or STAN and like go to way more trouble than I wanted to. So in situations like these, what I would probably be inclined to do, given that it's maybe not terrible, but I'm not quite sure, but the predicted values are staying in bounds, is to switch to robust maximum likelihood estimation. So that is described in Enders chapter 5, I think, is on your reading list for like this section or the next section. He talks about what happens in that. And basically there's a ratio that if data are multivariate normal, there's a ratio of the first derivatives of the likelihood and the second derivatives that should follow some form. And to the extent that it doesn't, that difference is used to correct the fit statistics of the model and the standard errors for deviations from non-normality. So I will be using that instead in the second half of the handout, in which we do these same models via path analysis. But just for looking at what's in the model here, any guesses as to why this is ultimately not going to be sufficient with respect to its fixed effects? What don't I have in here that I could have added? So I did Kid Boy on everybody, and we only needed this one, so that should probably be fine. I did dad's education on everybody. What about these two? Confidence interval? Is that a question, Farhan, or a comment?
Sorry, just ignore that.
Okay. Well, I had a question mark, so I didn't know how to interpret that. What about mom's education? Don't you think that should matter? If dad's education matters, shouldn't mom's education matter, like in theory? Turns out, spoiler alert, it does. So one of the things that we get out of path analysis is indices of model fit, which is not about distribution fit, and it's not about strength of prediction. It's about whether the model has adequately captured the relations that exist between all the predictors and all the outcomes. And we would not know from any of this that this model is not good enough. We just add fixed effects and we see if they're significant, and if they are, we keep them and we go about our business. But this doesn't tell us whether or not it's sufficient. So that's also one of the advantages of path models, besides more direct specification, more options for link functions that have variable-specific, modifications for their variance-related terms, so stretchy factors and that kind of stuff, is that we get indices that tell us if we're missing anything. So where we're going to end up is examining mom's education on extra things, but that's not going to happen until next week. So there's some words for you. All right, questions or comments so far? No, the exciting conclusion is part 2. I'll show you where we're going to end up with words, 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 code, picture. Have you seen pictures like this before? Yeah, this is a very classic way of describing linear modeling. It's called a path diagram or path analysis. And typically path diagrams go either from top to bottom or left to right in terms of how their arrows are depicted. So I have all of the predictors that we were considering on the left-hand side, the 3 boxes for the outcomes on the right-hand side. So this is another way of thinking about the same types of models that we've been looking at, is that we're predicting these 3 outcomes simultaneously. What I don't have in the picture here are covariances between these boxes. So 2-headed arrows that would capture their relationships. And I don't have anything resembling residual variances either, because I was just focusing on the fixed effects. So I have father education has been allowed to predict all 3 of these. Child's education and child's gender is only predicting their attitudes. And the part that we're missing then, we have this path right here, mother's education to their attitudes, but it turns out that we're going to need to put in those 2 later. So the process of figuring out how I learned that and then putting them into a path model and model for the multivariate stack data structure, well, that'll be next week. So, stay tuned. All right, lots and lots of code. Questions? Okay, I know what I want to go back to. I want to go back to my R matrix. 26 pages later. I'm insane, you know that? Has anyone ever opened my handouts and went, Lisa's insane? Like every single one is 30 pages long. It's a good thing that we don't do paper anymore, because I'd be responsible for killing so many trees. And color at printer ink, by the way, too. But this is what I wanted to look at. So this idea here of just letting each outcome have its own residual variance and have a residual covariance directly in the R matrix, I call this the direct way of introducing dependency. If any of these outcomes if any of them needed a generalized model instead, where the model does not have a separate residual variance, I can't do this. There is no such thing as an R matrix in generalized models, because if there's no residual variance, there's no residual covariance. So the one thing that we haven't talked about yet in Lecture 5 is what to do instead. The idea of a random intercept as a way of introducing relationship or dependency instead. Shall we look at that? Why not? And for those of you who are thinking, is this the same random intercept that Ariel talked about in design of experiments, and Jonathan talked about in clustered multi-level models, and Lisa talked about in longitudinal multi-level models, and she probably talked about in factor analysis? Yes, it is the same. Random intercepts and latent variables are also the same thing. So there are many points of intersection across all of the different classes because they're borrowing ways of addressing relationships between variables from each other. Okay. So we had, this is going to lecture 5 here, slide 16, that's where I'm at. So this was the strategy that I just used in this example 5a here. If I don't have very many outcomes, and if those outcomes are plausibly multivariate normal, then I can just let the outcomes have separate residual variances, let each pair of outcomes have a different covariance, fit this unstructured model. Now, where this falls apart is if there's lots of outcomes. Like if I tried to model 10 outcomes at the same time, then this would require 55 parameters to pull off, and odds are good that that would be too many relative to my sample size. The other way that this becomes, is not applicable, let's put it that way, is for unbalanced data. So balance versus unbalanced. Balance is the idea that there's the same possible set of outcomes for each sampling unit. So like if this is mom, dad, and kid, this is fine. If this is pre-test, post-test follow-up, this is fine. If this is repeated measures condition A versus B versus C, this is fine. But what if it was something like answer a question in the morning, answer a question in the afternoon, and answer a question in the evening? If you wanted to actually keep track of when people answered the questions because you thought time of day was relevant to the construct you were examining, odds are good that questions that are answered together that are closer in time are going to be more related than questions that are further apart in time. So ideally, in that situation, you'd want to have like exact time the question was answered as each separate row for this thing. So where you would end up is each person potentially would need their very own type of R matrix with different time entries. So that's unbalanced data, and that does not lend itself to fitting this type of structure. So this direct effects thing, in addition to being multivariate normal, only works when all of the data can be described by the same matrix in terms of its shape. People can be missing, but the same possible rows and columns have to be there. And the missingness is only allowed if you have maximum likelihood or residual maximum likelihood as opposed to least squares. The other two that I had presented that are plausible, and this is in one of the other examples that I'm not going to have time for. I go through some of these choices. You can do a likelihood ratio test to see if you can get away with something simpler. So this is compound symmetry heterogeneous. This is what this pattern is called, where each outcome would get a different residual variance, but they share a common correlation. And so this is one parameter. It's called CSH in the output in SAS, which is where I stole this notation from. That same correlation parameter is multiplied by the standard deviations of the variables that it refers to create the covariance. So the covariances still differ, but the correlations that create the covariance are the same. So this would save you 2 parameters because you'd only be estiming 1 correlation instead of 3. Compound symmetry is the bottom one. That would save you 2 more parameters because this also forces the residual variance to be the same across outcomes as well. This compound symmetry parameter, this is the thing that we can replace with a random intercept instead. All right. So that was where I showed you this once before, but let's look at it again. So another way of modeling dependency that can end up at the exact same place, but is more flexible for more different kinds of outcomes otherwise, is this idea of building in a separate place into the model for dependency to go. So this is terminology that I use in the longitudinal class, and I think in the cluster class to some extent, although it's not as big in terms of making sure that the structure is right because they don't have a design effect like time to worry about. But we have this thing that I'm introducing called the G-matrix. And in multi-level modeling notation, this refers to any level 2 variance terms, random intercepts and slopes, and R is still the level 1 residuals of what's left. So another way of asking a program to give you this compound symmetry structure is to do it this way instead. So rather than saying, I want an R matrix that has equal variances on the diagonal and equal covariances on the off diagonal. That's one way you can do it. That's requesting a compound symmetry pattern. You can do that in GLS, for example, in R. The other way to do it is say, no, I want a random intercept. And after I account for that random intercept, then I want the residual variances that are left over for each outcome to be the same and to have no relationship. So these two matrices get put back together again into a combined version that's called V. And note that I have plus and equals in quotes here because I know this doesn't work for matrix multiplication, but just bear with me. If you take this random intercept variance, this U term right here, and just like stick it everywhere in this R matrix, you end up with V over here. So if you compare this V on the bottom to this R on the top, they are exactly the same with different notation. I've still got sigma squared E, which is the variance of the E residuals. The CS thing is taken over by tau squared, which is the variance of these random intercepts. So the question is, okay, what is this U thing, and why does it get a variance? So the difference between a univariate model and a multivariate model that adds random effects for dependency would look something like this. Both of them can have whatever fixed effects you want. That's not the issue. We're focusing exclusively on what happens with the residuals, their variance and their covariance across sampling units. What happens when you add a random intercept? It's easiest to picture in the general linear model case, but this extends to generalized models as well, is that it takes the variability that was in E and essentially splits it. And it's trying to figure out how much of what is in E is constant to a person and how much of it is time specific instead. The sum total of those put back together again is the same. But what ends up happening is that U is a way to introduce a relationship between the E's indirectly because the E's are still independent. They're independent after you factor in this U thing. So I've got a picture here. I stole from my other class, of course. Let's say that I have repeated observations for my multivariate model that are time. This can be condition, can be whatever. And we'll say that we're fitting a model where we're expecting no change over time. That's my black line. So here's my purple person's data. This person is below the mean for the sample on every occasion. So their E's are going to be related as a consequence of that. What a random intercept does is take the total distance between the outcome that is predicted from the model for the means fixed effects and the actual outcome for this person, and it splits it. Instead of trying to cover the full distance, we try to figure out what the mean for that person would be, and U captures the difference between the fixed effect predicted mean and the individual person's mean. So this person being below everyone else would result in a random intercept, that's this U thing, that's negative. Somebody who is exactly at the sample mean would have a U of 0. Somebody who is above the mean consistently would have a positive U. From there, E is what's left. E covers the deviations from that person's mean specifically, with the logic that after you factor in the idea that this person is below average all the time, their e's should have constant variance and be independent. In other words, this random intercept is the source of dependency. Yes?
If we consider we repeat syntax this person and do we expect the variance of E will be equal to 0, which means the person will have the very stability theorem.
I only heard part of that.
Yeah, I was wondering, for the variance E part,
Mhm.
will be a person be tested at a different time point, right? What if I assume this person will be stably to respond each time,
Mhm.
and I make the assumption that the variance of E will be 0?
So we are assuming that the same U covers each person the whole time. So there's only one U per person, but there would be 5 E's per person.
Yes, and the variance E can I assume if the person is stable to respond, so the variance E equals to 0.
The variance of E would still be non-zero to the extent that people differ from their own means. The only way that you would not have E variance is if somebody gave you the exact same answer at every occasion.
Yeah, that's what I'm asking.
Okay,
Yeah, if we assume this person is stably to answer all the questions like
Mhm.
behavior at a certain level
Mhm.
or the ability at a certain level,
yes.
then there is only
Then there would be no E. Yeah, and so if that happened, if everybody gave you the same answer 5 times, you don't have multivariate data. You have one outcome. Because you have one outcome from the amount of information it contains. It would be perfectly correlated across time if everybody gave you the exact same answer. So if that happened functionally in longitudinal data, you actually have cross-sectional data. If there's no variability over time in what people said. But that's very rare. I have seen it before, but it's pretty rare. But the idea is that U is this term that we can put in the model that creates a relationship between a person's outcomes, and that relationship can be put in even if we don't have separately estimated residual variances, such as in general linear models. Yeah, I've got the matrix notation here because I felt like I would be derelict in my duties without it. So if we have, say, 3 outcomes per person, A, B, and C, back again in this, and I have this U and this E, the way that this would typically be described is this type of equation right here, where X is the design matrix for all the predictors that have fixed effects, beta is the matrix of fixed effects, Z is a design matrix for the predictors that have random effects, and at this point there's only one, it's just an intercept, and then U is the matrix that holds the random effects, one separate for each person, and E holds the per outcome residuals that are left. So the total variability is spread across these 2 terms instead of one, ZU and E. The dependency is in the U part. If this model is correct, typically what we assume is that the E's are independent with constant variance, because the only reasons for that violation would be over in U instead. So it looks like this if you actually do the matrix multiplication properly. The U variance that's in G gets pre and post transposed by Z to make it the right shape to add to R, and then you end up with this thing right here, which is compound symmetry. So if you have multivariate general linear model type data, this is a semantic distinction. Compound symmetry is the same thing as a random intercept model. You can specify it using different syntax, but it ends up at the same place. If you have generalized linear models where an R matrix is not a thing, then you end up needing to do it this way instead. So we're talking about then the linear predictor in a generalized linear model has the U part in it. Even though I consider that a variance term, technically speaking, it's included in the linear predictor. Because then the conditional distribution can be Bernoulli or binomial or whatever it needs to be, because it is independent at that point. all of the reasons for the correlation should be in this part of the model, in the U part. So then this is the only choice really that I know of for introducing correlations between outcomes in generalized linear models. So let me think. I think I'll go there very briefly. So for those of you in the IRT class, have you heard about bifactor models yet? No? Has anyone heard of them? Otherwise, a little bit? So the idea of a bifactor model is when you have a situation where some items have something else that they're measuring, and you don't want that something else, is usually the context. So for instance, if I have ratings about a child that I've collected from their teacher and from their parent, well, what I want to know about is the kid. But I had to ask 2 different people to get a reasonable picture of the kid in their school settings versus their home settings and whatnot. So I might have a general latent factor that I believe is responsible for all of the answers collected about a child, their disposition, their abilities, whatever I'm measuring. I might then have 2 what are called specific factors that account for the items being measured by asking the parent versus the items being measured by asking the teacher. Because if you ask the same person a bunch of questions, there will be a relationship just because they're the same person. So there's 2 additional factors that are introduced in that context to adequately model all of the dependency in the item responses, so that then the item responses are conditionally independent like they're supposed to be. You can think of that bifactor as doing the same thing sort of as this U. Go back to the picture. Way back. It's trying to introduce relationships between the items, not by letting the residuals be correlated, because in IRT that's not a thing in full information maximum likelihood, but just introducing dependency in another way as a factor. So a random intercept is the same thing as a latent factor, where all of the factor loadings are constrained to either 1 and the variance is estimated, or all the factor loadings are constrained to each other and the variance is set to 1 instead. Take your pick. So I have, as my very last example in this class, a path model where at the end of the path model are 2 binary outcomes. The only way that I could introduce a correlation, basically, between those 2 outcomes is what I wanted, was with a latent factor, a random intercept factor. So then the outcome conditional distributions are independent like they're supposed to after controlling for that latent random intercept factor, 1 or more. So there's not as much flexibility, but that's what you're kind of stuck with. There's more flexibility in an SEM or path analysis framework than a multivariate stacked data type of framework, though. So, trying to make the ties. By the way, that same sort of bifactor analysis is often called a multi-trait, multi-method type of design in the confirmatory factor analysis world, where you'd have method factors for who answered the question and trait factors for the construct that's supposed to be measured otherwise. So, anywho, let me exit out of this. I'm trying to exit out of this. There we go. 136. Questions? Comments? The faces I'm seeing look overwhelmed.
Sometimes you speak so fast.
Sometimes I speak so fast. I'm sorry. Yeah, this is like the time of day where the caffeine sort of hits me, and I just kind of keep going. So I'm sorry about that. But hey, I'm recording. You can slow me down to like 33 speed, and that will sound better. All right. Any questions before we call it a day? Otherwise, you won't be sad if we end like 7 minutes early. One last question as a parting gift.
Yeah, so the things that we covered today, this G matrix or G separate thing,
Yeah.
is related to the directly or an indirect?
This is the indirect effect, because indirect way of introducing dependency, because in this way of setting it up, you still have a conditional distribution that is univariate. So if there are residuals, let's put it that way, they are independent because all of their relationship is captured in the random intercept or random intercepts instead. So this is the indirect side. If you have multivariate normal data, it works out the same either way, but the random intercept option is the only choice if you have generalized linear models that you need, or you have unbalanced data, where you can't just say let the R matrix be what it wants, because each sampling unit would have a different R matrix structure, and that doesn't work.
Great, thank you.
And random slopes then introduce heterogeneity of variance as a function of a predictor, but they also introduce a further source of dependency. So like if people change differently over time, then you also need what's known as a random slope for time that allows each person to have their own deviation from the growth rate of the sample, and that introduces a second layer of dependency in how their outcomes are related to each other, beyond just the intercept. So it gets more complicated, but that's the other classes, point being. Random effects for dependency, that's my tagline. How's that? / latent variables. All right, shall we call it a day? So it's Thursday. That means I say have a good weekend. Good luck with all of your projects, papers, tests, and whatnot. Hang in there. Let me know if I can help you with anything.
Thank you.
Thanks for being here.